Hello and welcome. In this video, we're going to talk about how to solve a polynomial equation using the rational root theorem and using synthetic division. So our goal is going to be to find all of the values of x that make a polynomial equal 0. We're also going to extend this idea to graphing. If we know the x values that make the polynomial equal 0, then that can help us graph because it tells us where our polynomial function is crossing the x-axis. So let's go ahead and jump right in. So when we learned about quadratics, we learned a bunch of different strategies for us to solve a quadratic. We learned the quadratic formula, factoring, complete the square, square roots, and now we're going to use that foundation to help us solve a polynomial equation. So we're going to start by solving using factoring. So go ahead and pause the video and factor this polynomial on number 1, starting with the GCF, and then factoring completely, and then unpause the video and see how you did. So if you factor completely, you're going to get 2x as your GCF, and then you're going to have x squared minus 6x plus 9, which factors to be x minus 3 quantity squared. So then you're asking yourself, what makes 2x equal 0, and what makes x minus 3 squared equals 0? Because the zero product property tells us the only way to multiply two things to get 0 is for one of those two things to be 0 itself. So in red, 2x is 0 when x is 0. And in black, I can square root both sides. X minus 3 is 0. So this is true when x is equal to 3. So our solutions here would be 0 and positive 3. And what I want you to notice over here on the right-hand side is we actually have the graph of the polynomial function who has these zeros off to the left. And notice that we had this squared sign happening here, and that's called a double root or a repeated solution. Because x equals 3, really, there were two different ways. We could have rewritten that as x minus 3 times x minus 3 equals 0. So there's two 3's in this sort of solution set. It seems silly to write it twice, but what's interesting is that tells us a little bit about the graph. If we have a double root or any sort of even root, that means that the graph touches the x-axis at that point, but it doesn't cross through. So you'll see here, it comes down, it touches the graph at x equals 3, and it goes back up. It turns around at that point. It's like a little vertex. It does not pass through the graph. As opposed to x equals 0, which was not a repeated solution, if we have an odd power, so even if I had x cubed times x minus 3 squared, this would be an odd root, still a repeated solution, but to an odd power. That means that it crosses through the graph at that value. Now, if it was a cubic, it would look a little different when it crosses, but odd powers are going to cross right through the axes. So why is this important? Well, first of all, it's great for us to spend some time reviewing factoring so that we can identify what these zeros are. Being able to identify what they are gives us points that we can plot on the x-axis when we're graphing. Knowing if they are a repeated solution or not tells us a little bit about how it's going to look when we graph it. We now know if it's a double root or an even root, that means it's going to pop back in the same direction it came from. It's not going to pass through. And if it's an odd power, it's going to pass through. So let's tie this to graphing a little bit and review what we've learned about graphing polynomial functions before. So let's talk about some tips for graphing first. The first thing that we're going to do is, if possible, which it will be on these two problems, if it's possible, the very first thing that we're going to do is we're going to factor to find the roots. Those are the places where we're crossing the x-axis. We're going to identify if they're repeated or not, and that's going to tell us how it looks. Does it pass through the x-axis at those values, or does it bounce back up if it's an odd or if it's an even root? Then we're going to plot those values on the x-axis. We're also going to pay attention to the end behavior. Is it even? Does it point the same direction as it goes to infinity and negative infinity, or is it odd? Is it the leading coefficient positive or negative? What do those key things that we've already talked about in previous lessons tell us about the graph? Does it have, or what is the y-intercept? Now, sometimes the y-intercept is just going to be one of those zeros that we already found, but sometimes the y-intercept is going to be something different. That's an easy point to plug in a value for and plot. Once you have that plotted, you're going to have some points on your axes, and we need to figure out what's happening in between those points. So you can make a table or you can just plug in values, but we want to find points in between our zeros, and we're going to graph whatever fits on the graph. And even if something doesn't fit, it still tells us a bit about the shape of the graph. So let's work through these steps on these two problems. The very first thing we're going to do is factor. So I'm going to set this equal to 0 so that I'm finding the zeros, and I'm going to factor. I notice that the greatest common factor here is 2x, and if I factor 2x out, I get 2x squared plus 7x plus 3, and that looks like it's going to factor more. 2x times x, I need 7 in the middle when I multiply to be 3, so 3 and 1. So I can find 3 zeros here. 2 times 0 is 0. If I set this equal to 0, I'm going to get -1/2. And if I set this equal to 0, I'm going to get -3. None of those are repeated. So I'm just going to write none are repeated. What that means is our graph is actually going to pass through the x-axis at each of those 3 values. So I'm going to plot a point at 0, 0. I'm going to plot a point at 1/2, 0. I'm sorry, at -1/2, 0, and at -3, 0. And you could change your scale factor if you wanted to make it a little easier to put -1/2, 0 on there, but I'm going to just leave it like this. So we accomplished our first step, factor to find the roots, decide what kind of roots they are. So each of these points, when we get to them, we're going to pass through them. The second thing on our to-do list is to identify the end behavior. Well, this is odd. It has an odd degree, and the leading coefficient is positive, so it should look something like this at the ends. So at the end over here, it should be going up. At the end over here, it should be going down. I'm not necessarily going to connect to those arrows, but I'm going to use those as a guide to make sure my graph behaves the way that I know it behaves based on that end behavior. Then I'm going to find the y-intercept. If I plug in 0, I get 0, and that point's already plotted. So in this case, that wasn't super helpful for me. And then I'm going to make a table to figure out what's happening between these values. So I want to know what's happening to the left of -3, so I'm going to plug in something like -4. I want to know what's happening in between -1/2 and -3, so I'm going to plug in something like -1. I don't really want to plug in a fraction, so I'm not super concerned about plugging in something between -1/2 and 0, but I could, if I wanted to, plug in a number like -1/4, and then I want to plug in 1. So I can see what's happening. I may need to plug in more numbers than this. I may not even be able to fit these numbers on here, but this is where I'm going to start. So go ahead and pause the video and work through plugging in those 3 values to your function, and then unpause the video and see how you did. So it looks like when I plug in those values, only one of them fits on the graph, and I'm actually kind of curious what happens at -2, so I'm going to plug that in as well. If I plug in -2, I'm going to get -32, 4 times -8, plus 14 times 4, which is going to give me 56, minus 12, 6 times 2. So if I combine those, I'm going to get 12. So that's going to go off my graph quite a bit. Okay, so I know that -4 does not fit on my graph, so I better make sure when I'm drawing this line, I'm not going past where -4 is. It needs to be narrow because -4, -56 definitely doesn't fit on this graph. Now, -1, +4 does fit on our graph. And actually, I'm going to undo that line. It's going to be easier to connect with it. Not there. And I know that -212 doesn't fit on the graph, so I'm going to make a little note to myself. That should be somewhere up there. And then +1, 24, isn't going to fit on my graph, so I'm going to make sure this goes up and is really skinny. So I'm going to connect the dots with that end behavior in mind, but also staying really narrow to make sure that I'm not crossing over a value that's not there. So this should go way up. What's happening between these 2 points? Well, it's supposed to go through, so I guess it's going to look something like this. Hopefully a little smoother when you're writing on paper and not on an iPad. Okay, I want you to go ahead and look at number 3, and let's start with factoring. So let's set it equal to 0. negative 1/2 x to the fourth plus 4x squared minus 8. So the first thing I notice is that this doesn't look like something I know how to factor with this negative 1/2 in front, but maybe if this negative 1/2 wasn't in front, it would be easier. So I'm actually going to factor out negative 1/2. That's going to give me positive x to the fourth. If I divide 4 by negative 1/2, that's the same thing as multiplying by negative 2. That's going to give me minus 8x squared. Or if you think about it, if I distribute this, I'm saying 4 is half of whatever I need to write here. So that's going to be negative 8. Negative 8, if I divided that by negative 1/2, that's the same thing as multiplying by negative 2. I'm going to get 16 here. And what's interesting about this is that I actually do know how to factor this. This is a perfect square. This is x squared minus 4 quantity squared. And I actually know that this factors as well. So this is going to be negative 1/2 times x plus 2 times x minus 2 times x plus 2 times x minus 2. So let's just write those as perfect squares here. So what are my roots? Well, my roots are when x equals plus or minus 2, and they are both double roots. What that means is it's not going to cross the axes at those two values. So let's go ahead and plot those two values, positive and negative 2. Let's identify the end behavior. This has an even degree, and it's negative. So at both ends of the graph, it should be going down. Let's find the y-intercept. If I plug in 0, I get negative 8. I don't think that's going to fit, but it's going to almost fit. 1, 2, 3, 4, 5, 6, 7. So it would be around here. I'm just going to add that point there. And then I'm just going to make a table to try and find a couple of values in between. So I want to know what's happening to the left. So negative 4 in between them. So negative 1, positive 1. Actually, instead of negative 4, no, I like negative 4. I'm going to pick mostly even numbers here, if at all possible, so I don't have to deal with that fraction. So negative 4, negative 1. So I picked one number to the left, one number in the middle, and now I want to pick one number to the right. So I'm going to pick positive 4. Go ahead and pause the video and plug those values in. All right, so definitely 4 and negative 4 aren't going to fit on the graph, but negative 1 and positive 1, I can fit both of those values on the graph. When I plug in plus or minus 1, I get negative 4.5. So 1, 2, 3, 4.5. And now I'm going to connect the dots, keeping in mind the end behavior and remembering that I am not going to cross the axes when I get to those zeros. It's going to pop back down sort of like the vertex of a parabola. So I'm going to keep this really narrow. And I'm going to connect and keep this really narrow. So it sort of looks like an M. So we'll practice more graphing later in a different video, but the idea here is that we just learned a new tool that we can add to our toolkit for graphing to help us out. Now let's talk about how to factor something that maybe we're not quite so sure how it factors, or how to use synthetic division to help us factor a polynomial function. Okay, sometimes it's not so obvious how something is going to factor. For example, we've talked about how to factor something with 4 terms by grouping, but what happens if grouping doesn't work? What happens if there's 5 terms or 6 terms? Then we may not actually be able to immediately jump into factoring. So that's where the rational root theorem comes in. What the rational root theorem says is that for every polynomial function, or for the zeros of every polynomial function, they will be of the form P over Q, where P is the factors of all of the constant term. So let's just write an example up here. F of x equals 2x squared plus 7x plus 1. So in this case, P would be all of the factors of 1, which are 1 and negative 1. Those are the only things that multiply into be 1. Let's write that in red. And Q are all of the factors of the leading coefficient. So over plus or minus 1 or 2, because those are the factors of 2. So all of the possible rational solutions will be of the form factors of this over factors of this. So that gives us a starting point, not the greatest starting point in the whole world, but we know a lot of math foundations that'll help us out along the way to help us figure out what a possible factor is. So this theorem gives us a list of possible rational solutions. We still have to test to actually see which ones are real, meaning we're going to use synthetic division to determine if the remainder is 0, like we did in the last video. So let's go ahead and look into this. The very first thing that we're going to do is we're going to list our P's and Q's and list our P's over Q's. So in this case, P is 20. So we need all of the factors of 20. So I'm going to just write 1 plus or minus in front. What goes into 20? 1 and 2, not 3, 4 and 5, not 6, not 7, not 8, 9, 10, and 20. Those are all of the factors of P. Then we're going to list all the factors of Q, which Q is just 1, and the factors of 1 are just plus or minus 1. So then we can list all of these as a fraction. P over Q is plus or minus all of those numbers divided by 1 are really just all of those numbers. If there was a 2, if Q was plus or minus 2, we'd also have to think about 1/2 and 5/2. But this is what we have for our options here. Now that we've accomplished that, we're going to try and figure out using synthetic division what we should guess or what we should test first. So the first thing I always like to do is 1 and -1 are pretty much always going to be an option because they're a factor of everything. So I usually just in my head mentally plug in 1 to see if it looks like it's going to work. 1 minus 8 plus 11 plus 20. Does it seem like that's going to be 0? Not really. 1 minus 8, -7 plus something really big. That doesn't seem like it's going to be 0. So I'm going to skip over testing +1. That means maybe I see 11 and 20. Maybe if there was a negative sign going on here, maybe that actually might work. So I'm going to choose to test x equals -1. Now, I'm intentionally going to pick problems where you shouldn't have to guess 50 numbers before you get a correct one. But let's see what happens when we use synthetic division with -1. So I'm going to write -1 on the outside. I'm going to write the coefficients, 1, -8, 11, and 20. I'm going to bring 1 down and apply my synthetic division. And, well, that's awesome. I just got a factor. So the first thing we just figured out is that x equals -1 is going to be one of our solutions. Now, we could keep doing synthetic division again from here, or we can see if what is left is easy to factor. Well, this was a cubic, which means this new expression is going to be a quadratic. We can set that equal to 0. We can now solve this by factoring. X squared minus 9x plus 20. Well, x squared is x times x. I want something that multiplies to be 20 and adds to be -9, so -5 and 4. So that's going to give me 2 more zeros, 4 and 5. Let's pretend that this expression gave us something that was not easy to factor. We could continue working through with our P's or Q's. But the beautiful thing about getting down to a quadratic is we know how to solve quadratics. Whether we have to use the quadratic formula, factoring, complete the square, any of those things, we already know how to solve a quadratic. So if you get down to a quadratic, you may want to factor. So again, what we're doing, we're listing our P's and Q's. We're figuring out if something is or is not a factor. We got a factor on our first try there. If it is a factor, either factor what's left, that's what we did in purple, or use synthetic division to try and find a simpler polynomial. Don't forget to list off each answer you find using synthetic division, and then have your final answer in set notation. Okay, let's look at number 5. So let's list our P's and Q's. I'm going to come up here so I have a little bit more space. Things that are factors of 24, 1, 2, 3, 4, 6, 8, 12, 24. Lots of numbers there. Q, I just want to point out, is again plus or minus 1. That's the leading coefficient. So our P's over Q's are just all these values, and I don't really feel like rewriting them. So again, I'm going to look and see right away, does it look like 1 is going to work? 1 plus 1 minus 14 minus 24. It doesn't seem like that's going to equal 0. If I plug in -1, Let's see, -1 plus 1. Maybe, I'm not sure. It doesn't look like it's going to work, but let's test it anyways. So test x equals -1. So coefficients 1, 1, -14, -24. If I bring this down, I'm applying my synthetic division. This is going to give me -10. So this is not a factor. So -1 is not going to be a 0 or a root. So I'm going to test a different number. So let's pick something else. How about +2? If I test +2, 1, 1, -14, -24, I'm going to get 1, 2, 6, -8, -16. That's not, I don't even care about simplifying that. That's not going to be 0. So 2 is not a solution. Let's try -2. Now, again, I'm not going to make you try, hopefully, too many numbers if you choose logical choices first, but this one is getting us a little bit here. -2 times 1 is -2. If I add up and down, I get -1. This is going to give me +2, so -12. Ooh, 24 and -24. We found one. Okay, so the first solution that I just found is -2. What's left, since this was a cubic, is going to be a quadratic. So let's go ahead and write that out. X squared minus x minus 12 is going to equal 0. That factors x minus 4, x plus 3, which means I just found 2 more zeros, +4 and -3. Okay, we're going to do 2 more problems together, and then that's it. Okay, here we go. I'm going to encourage you to pause the video and list your P's and Q's. Not your P's over Q's, just your P's and your Q's. Okay, so P is 18 or -18. So factors of 18, 1, 2, 3, 6, 9, 18. Q is ±2, which means we have the factors 1 and 2. So if we're listing our P's over Q's, we're going to have, well, if I divide each of those things by 1, I just get what I started with. If I divide each of them by 2, I get 1/2. 2 divided by 2 is 1. I already have that. 3 over 2. 6 divided by 2 is 3. I already have that. 9 over 2. 18 divided by 2 is 9, so I already have that. So these are all of my possible factors. Now, it's going to be really unfortunate if we have to test all of those, and I definitely don't want to start with my fractions, but what I want you to notice is when the leading coefficient isn't 1, we have a lot more options, which could be good or could be bad. Okay, so let's see. If I check 1, 2 plus 5 minus 9 minus 18, that doesn't seem like it's going to work. So let's test -1. So -1, 2, 5, -9, -18. I'm going to bring my 2 down, -2, 3, -3, -12, +12. That's not going to work. So -1, not going to work. Let's test x equals 2. I'm just going to come down here, 2, 5, -9, -18. That's going to give me 4, 9, 18, +18, so +9, so +18. Yay, we found one. So the first answer that we just found is 2. Now what's left is going to be 2x squared plus 9x plus 9 equals 0. Does it look like this is going to factor? I'm not sure. Let's see. 2x squared is 2x times x. 9 is 3 times 3. Everything's going to have to be positive. Let's see if this works. 3 plus 6 is 9. Awesome. That worked. So x is going to equal -3 over 2 and -3, which both would have been on our list. So if we weren't sure that that factored, again, we could have used the quadratic formula, but we also could have just kept using synthetic division until we find the solution. All right, I want you to try and work through number 7 all on your own. List the P's, list the Q's, list your P's over Q's, and then start working your way through. Then unpause the video and see how you did. So here are all of my P's and Q's. It doesn't look like 1 is going to work. 3 minus 8 minus 15 minus 4, so I'm going to start with -1. Oh, awesome. -1 works. That's going to be my first solution. Now I'm going to rewrite what's left as a quadratic and see if it factors. And it does factor. So we can find our two solutions, -1/3 and +4. And we can write our final answer using set notation. All right, so let's recap what we covered in this video. We reviewed a bit on factoring in the last video, and then we used factoring to find the zeros or the roots of a function in this video. We talked about how if we have a repeated root or a repeated root to an even power, that means it touches the x-axis that place and then goes back in the direction it came from. If we have an odd repeated solution, meaning to the power of 3, to the first power, to the fifth power, then it crosses through the x-axis at that value. And we used that to extend how we graph. We added it to our toolkit of graphing. So we found the zeros, found the y-intercept, used the end behavior, and made a table of values to help us connect the dots. Lastly, we talked about the rational root theorem and how we can use that theorem, identifying our p's, the factors of the constant, and our q's, the factors of the leading coefficient, to create a list of possible rational factors and how to check those using synthetic division so that we can factor completely. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.